Okay.
Goes in a pocket.
Thank you. You know, I suppose that the discussion should go to the future, and I'm going to speak about the past. So I'm sorry, but yeah, but I can justify it only by my age. That no, indeed, I was thinking that I'm kind of not very much involved in this kind of development, which was mostly discussed here in this workshop. But I decided that I'm still following this G-2. I mean, and it is kind of one of the few stuff which is going experimentally now. So that's why I mean, I think that it's not that much of choice for this part, and as you know, that it was no, it's a long story, right? That people measured this anomalous magnetic moment for mu, and it was different from expectation, and it's kind of one of difficult to count what year it was, but I think that here it is. Okay, it's partly kind of praise of lattice which going on because what I'm showing here is a reference to BMW study of the problem of G calculation for G-2 on the lattice. No, I would say that it's not just G-2. Okay, in certain way, it's just essentially calculating the lattice a plus and minus into hadrons. But G-2 is explicit application, and why I was very much impressed by this calculation that they says that their accuracy better than %, which is needed for G-2, so it's like at the level of 0.5% accuracy, and that and it is what I believe it's from their paper. Look, here you can see results. This the first measurement of in BNL G-2. I need to remember what year it was. 90. I mean, it's pretty long. No, it's probably more than 1,000, right? But it's pretty long. That's a more recent one. It is in Fermilab, and they are going to improve the accuracy actually. So it's there on this stage. At the moment, as you see, they are consistent with this old measurement, more or less. Okay. Sorry. Yeah. Yeah, right, right. But the idea of Fermilab measurement is that they improve it a few times, make it a few times less. I mean, the error. So at the moment, yeah, okay. What was claimed as a standard model prediction? It this greenish one, and as you see, it is for sigma in terms of predicted value from measurement, which is sounds pretty substantial. And what was kind of unexpected result of lattice calculation was that they calculated this a plus and minus of the hadrons on the lattice, and you see that the result is, I don't know, 1.5 sigma away from experimental value of G-2, but 2.5, no, not 1.5, more than 2 sigma away from direct calculation of based on a plus and minus into hadrons. Okay, so I mean, what it means as this type of claims that what people measured that people who measured E plus and minus into Hedon, that their cross-section is less than expected from this latest calculation. And numerically, maybe it's not that large effect because we are talking about, in terms of hadronic contribution, it's like 3% of hadronic contribution. So it's not a big portion of it, but still the claim of experimental claim of E plus and minus to Hedon was that they have accuracy better than %. So in this way, it's, I mean, it certainly was not 3% an error. So this looked very serious. What was more recent this year, it is it's a measurement, new measurement, non-result of Novosibirsk. Okay, I didn't put the name of the authors here, but it is a paper of February 17 of this year. And it is the same people who measured, I mean, E plus or minus or Hedon before. So it was CMD2, director, and some in other one. Okay, here it is just a mu, which is G minus 2 divided by 2. That no, just to show that it's just integration of observable cross section. KOS is known function. Okay, so here it is their statement. So you see that this measurement I'm talking about, the lowest one, CMD3. Okay, and it is essentially kind of shifted to sigma to the same direction. So they are now kind of in the range of this what BMW predicted. So and much closer to, as a result, becomes much closer to experimental value of G minus 2 as well. And for me, it was particularly impressive that, you know, I don't know, for me, it's the first time that the lattice was predicting something before measurement. So okay, Jeff, it's pretty impressive. We talk about this. No, I mean, because I've always had some doubts about accuracy of lattice, right? But here it is kind of demonstration of real ability. I'm not sure there are. I don't. It's not many competitors to Novosibirsk in this. It is a range of energy, as written here. You see, it is essentially a range below 1 GeV. It's a low meson. So where the increase was. So it does not change data for higher energies. But most when I talk with authors of this, they do not know what is the reason why their previous measurement was less, but it looks like kind of effectiveness of detector is improved, and they are much more kind of much more belief in this recent measurement in terms of you know. Say it. Yeah.
Was this blind?
I'm not sure how blind they were. So this internal technique. No, but when I talk with particular person who is one of these authors is Sasha Bonder, and he's very good physicist. So no, I mean the one whom I would trust in his judgment, and he did say that. He doesn't know what was, you know, kind of, was it, but no, there's some number of problems. When I am saying that this error is less than %, they are saying it's 0.7%. It is mostly systematic error, and you know, the systematic error is, I mean, it's not about statistics essentially. You know, it's you should be kind of understanding a lot to be sure that nothing happened, right? But okay, but anyway, okay, it's the facts which this story which I was impressed very much to the extent that I decided that you could be interested too. That's it.
If you take CMD3.
Yeah.
And plug it into the lattice, then it moves to the input.
No, I mean that they already kind of very close to what lattice predicted. With this new measurement, gives them the value that I think that within 1 sigma they are with the lattice.
So my understanding is that the white paper average, right, it had a larger, had a big input from this plus or minus.
Yeah, right. So it was both on Z, right?
PFW did not.
Yeah, right. So the difference is that white paper was based on the previous. Everything which above the CMD3, was of course included in white paper.
Right. Well, PFW did a.
Right. No, I'm not talking about other sources. Like I was involved in this kind of electroweak correction and also kind of light by light, which also enters G-2. But the largest part it is this hadronic part. So and this lower energy range is more than a half of all hadrons. So it's a major portion of hadrons sitting below. Okay.
Give him the mic.
Sorry, yeah. I see. So I'm not only talking. I have a punishment as well.
Okay, where is
Here it is.
actually I meant my slides.
Yeah.
So I put it like here somehow.
I'm not sure.
There we are.
So just use the arrow buttons to move.
The arrow button. Okay.
You can sit around.
All right. Well, once again, thanks to the organizers, because it's a lot of fun. Just to start out with history. I've been coming to confinement meetings since I could walk. And, mostly they are, in the old days anyway, they were mostly about confinement mechanisms. I'm old enough to remember Merons. Anyway, there's a list. It's not even complete. And people are still coming up with various things. And I won't pretend to be neutral. I have my own opinion about what's correct. But, the sad thing is that not everybody agrees with me. And, the fact is that there's no general universal acceptance of what is really the confinement mechanism. And I think one has to admit rather bleakly that except for, some wonderful analytical stuff here, progress in this has been very, very slow. I think that's the honest statement. So I've been trying to think about, or I've been led to think about, some other rather general questions which are kind of related to these things. So first of all, it's this. We use this word confinement. What does it actually mean in QCD? In any theory where you have matter in the fundamental representation. Because when you have matter in the fundamental representation, you've broken center symmetry explicitly. So then what do you mean? What kind of order parameters have you got? What do you actually mean by confinement? And many people would say, well, confinement means that you have a color neutral spectrum and you have a mass gap, and that's it. Well, those are also features of gauge-Higgs theories. They also have a color neutral spectrum. They also have a mass gap, at least some of them. So is there no difference at all? Again, some people would say, yes, there's the Osterwalder, Seiler, Friedkin-Schenker, Banks, Rabinovich's theorems. that say that you can go from one confinement to Higgs without going through any phase transition. Nevertheless, they seem physically quite different. For example, in the confining theory, you have linear Regge trajectories and things which indicate that you form a flux tube. Engage here, Higgs theories, you don't. Is there any way you can make that precise, that difference? That's one question. Another question, if you open up a textbook on quantum field theory, there's usually a chapter or at least a section which is entitled Spontaneous Breaking of Gauge Symmetry. Well, there's no such thing. I mean, there's theorems that say there's no such thing. Nevertheless, is there perhaps some sort of symmetry which does distinguish between the Higgs phase and the confinement phase? That's another question. And this one I'm going to leave for a little bit later, not much later. We heard about these questions actually from one of the speakers yesterday. And also some people in the condensed matter community have been weighing in on this. I have my own views, so I'll tell you what they are. At the very least, the fact that different people are having different ideas, it's an interesting question. It's maybe the main message. But these are my views on the subject. First of all, let's ask, what do we mean by confinement in a pure gauge theory, where we think we know? I'd like to phrase it this way. Let's consider, say, psi naught is the vacuum, and we create a state. Here's a quark, a static quark. Here's an antiquark. These are just sources. And then we have to put some operator in between them to make the state gauge invariant. What happens as we pull the quarks apart? Well, let's say that the energy, we'll call it EV of R. Now, this energy is going to depend on this operator V. And I think the statement that we can say about whether we have confinement or we don't is that this energy must go to infinity as the quark sources are moved apart, no matter what V you choose. Whether it's a Wilson line or something else, doesn't matter. It goes to infinity. If it goes to infinity, and only if it goes to infinity for any V whatsoever, then you can say that we're in a confined phase. So that's one way of stating what confinement is in a pure gauge theory. Now, what we would like to say is that this is a perfectly good criterion in a theory with matter also. We use the very same criterion with one strong restriction. This operator must only depend on the gauge field, not on the matter fields. If you throw in matter, it's trivial that this wouldn't work. So the idea is you're basically constructing states where you've excluded string breaking. You've got quark and antiquark, you've got some glue in here somehow. And if a state like that, if its energy is going to go to infinity as you pull the quarks apart, that's a confinement, that's a gauge Higgs, or that's a matter theory, gauge plus matter theory, in the confined phase, if we can say. The second question. B is bicovariant, precisely. V is simply a function of the gauge field which transforms bicovariantly. That's the only thing. Highly non-local. It has to be non-local. Not at all. Not at all. For example, in electrodynamics, just ordinary electrodynamics, pure quantized Maxwell field. Line operator is allowed, but it's not the only kind of thing. For example, in electrodynamics, Dirac showed us a long time ago what kind of operator you would put so that you could pull these things apart, and the energy would go down like, would go like 1 over R, okay? You can construct operators like that in electrodynamics. You could construct operators like that in non-abelian gauge theory. However, in a pure gauge theory, it would still go to infinity, even if you did what Dirac did. Also in electrodynamics, if you made it a line operator and you pulled it apart, the energy would go up linearly. So it's going to be like that. So that's why it's rather crucial to make these statements about every single V. No. If you made a state like this, it would instantly decay into mesons. But that doesn't matter. The point is, these are states in Hilbert space. The fact that they would behave like this, of energy above the vacuum, of course, yes. No, it doesn't. This is I should have said this is an expectation value. Yeah, that's an expectation value.
Not reflected here, right? Because also you took a state where all additional pair was produced by the direct.
That's right. And what I'm saying is that if you take, say, a gauge-Higgs theory, or for that matter, QCD, essentially a theory with a property like this is going to, quote unquote, want to create a flux tube. And the only reason it doesn't create a flux tube is because it breaks, of course, by pair creation. But in the Higgs phase, by contrast, you can pull these things apart. You can pick some V, and it won't go to infinity. There are V's which avoid that. Okay, so the second question, the Higgs phase. I don't have time to do details at all, but what I want to say is that the Higgs phase of the gauge-Higgs theory is closely analogous to a spin glass. And in fact, there is, like in the spin glass has a global Z2 symmetry, for example, which is broken in the spin glass phase. There's also a global symmetry here. You could call it, say, the global center subgroup of the gauge group, which, by the way, doesn't transform the gauge field, but it does transform the matter fields. The statement is that in the Higgs phase, what we'll call the Higgs phase, this symmetry can be spontaneously broken. There's an order parameter for it, which you can construct by imitating what's done in spin glass theory. It's called the Edwards-Anderson order parameter. It does not imply a thermodynamic transition, but it does imply a spontaneous breaking of this. And remember, it's a non-local operator, so it doesn't necessarily imply a thermodynamic transition. But there is a transition. Now, the punchline is that the transition to the Higgs phase in this sense and the loss of confinement in this sense coincide. You can prove, for example, here, the strong coupling expansion, you can prove that you have this kind of confinement criteria. And you can also show numerically that in other parts of the phase diagram, you don't. So you know there's a transition between the two. You also know there's a transition here. A non-local order parameter. I would really have to define it for you, but what it really involves is this. You let the gauge fields fluctuate on a time slice, and you calculate the you don't fix them. Okay, so you have some thermalized configuration on a time slice. Then you let the Higgs fields fluctuate in that background. And you calculate the expectation value of the Higgs field at each point. At each point, it could be 0 or it could be non-zero. Then following what Edwards and Anderson do, you can define this order parameter. Now, it's non-local because, yes. No, the order parameter, excuse me. The order parameter is going to be a functional. It depends on the gauge field everywhere. Okay, on the time slice. It depends on the gauge field. That's what makes it non-local.
No, he's summing up spins average in different forms.
That's right. Yeah, well, you average over the whole lattice, of course. Yes. This would require, I'd have to go to the whiteboard. You can ask me afterwards. Okay, so anyway, that's the bottom line, that these transitions coincide. They do not imply, because that would contradict Fradkin, Schenker, Osterwalder, Seiler, and so on. It doesn't imply a thermodynamic transition, but the physics does in some sense change. In what sense? In this sense.
But the transition in what? In the transition, the transition temperature, right? And it could be that even in your scheme, there is no phase transition as function of temperature, right? Because you can be in confinement phase or in Higgs phase, and don't have any transition between them as function of temperature.
Yeah, although I must confess, I haven't studied the temperature dependence. No, the phase diagram, of course, let's make it simple. Let's say that there's two parameters. One is the usual Wilson coupling beta. The other one we can call gamma. You can think of it, let's say that the Higgs field has a fixed modulus, and then gamma is basically, well, it's a Higgs coupling essentially. So you have this beta gamma phase plane. In some parts of that phase plane, you're in the confined phase. In other parts, you're in the Higgs phase. That's basically what's going on. The phase diagram, and I'm using too much time, but looks something like this. You have, what is it, beta here, gamma here. There's a thermodynamic, this is for SU2. There's a thermodynamic transition here. It stops somewhere. Here you have the confined phase. Here you have Higgs. This order parameter will distinguish between the two phases, even when you stop having a thermodynamic transition. Okay, let me, yeah, but this isn't. I'm not even sure about that. I'm not so sure that experimentally they're so clear on that even. I could be wrong. Anyway, let me go to the next point because I should finish up. It kind of follows from this in a nonlinear way. But anyway, let me remind you of what Bastian Brandt told us yesterday, which is that if you're in a pure gauge theory and you have a quark source and an anti-quark source, of course you have a flux tube between them. And the flux tube can fluctuate. And you have a spectrum of possible states. Well, I can ask the same question in a gauge Higgs theory. After all, you don't have a flux tube, but your sources are certainly surrounded by gauge field, and it's surrounded by Higgs field. And that makes it a kind of a composite system. And in quantum mechanics, just about any composite system has a spectrum of excitations. So why couldn't these? If this would be true, then what we call some elementary particles anyway might exhibit a spectrum of excitations that would look like different particles actually. And we have done some computer simulations of this where you have static sources and it's possible to measure, whether it has excitations or not. And there does seem to be an excitation spectrum. I think the easiest place to look for it might actually be in superconductors, because that is a gauge Higgs theory, basically. The effective theory is a gauge Higgs theory. And well, thought a little about that, talked to a few experimentalists in that area. The experiments that might tell us have not been done, it seems. That's the situation, so I'll stop there. Yeah.
I think about the difference between the requirements. Put a boundary in the system.
Mm-hmm.
I don't know how. Here's the boundary.
Yes.
And on the boundary, the gauge symmetry becomes the global. And that's where that global.
Yeah, you could. I think this is where the condensed matter people are coming from. Yeah. I think they are thinking of it in these terms, putting some boundaries in and seeing what's going on in the boundaries. I can only say I haven't thought about it.
Does that say anything about the bulk applications of the bulk?
It doesn't say anything about the phase of the bulk, but it told something about the phase.
Yeah, that is the point of view of these condensed matter people. They're saying that if you put these boundaries in, then somehow what's going on the boundaries will tell you whether you're in a Higgs phase or some other phase. I think that's what's going on with that.
There's also potentially another criterion. If you populate the system with one variable, variable with overall momentum 0, spectrum of that single baryon state would be either continuous or gap, because the constituents would fly out and have individual momenta in one state.
You're talking about a mass gap, basically. That's what it sounds like.
No. So you populate, you create one baryon state, one baryon number state. So
Hmm.
that's three quarks.
Hmm.
And if they're confined, then that ground state is not gap, because it's confined in the zero momentum. But you could have relative momenta in the deconfined states, and then you would see a spectrum of these relative momenta, continuous spectrum on top of the one baryon chart in the deconfined. I think actually some condensed matter physicists think of deconfinement in some spin systems exactly like that. They look at the spectrum of a minimal excitation.
Mhm.
No, but add a chemical potential to that.
That's going to produce a state with, I'm going to make one variable.
Well, I mean, in some finite system, in some finite forms,
Mm.
just prepare a state with one. It's a quantum number. Prepare a state with exactly quantum number one. Okay, just one value.
Yeah, that's going to be the question.
Let's say you're talking about this, as about pure. Nowadays, everything could be checked on the latest. Right? We do not need any experiments. So can you check on the latest?
Oh, I said so. I have checked on the lattice. And indeed, there are such excitations.
Okay, so
We got a paper out on it.
standard of the day, it's enough. It's instead of experiment.
Well, I haven't gone so far that I think its experiment is completely irrelevant. It wouldn't it be nice to see it in a real physical system? Yeah.
Okay, I'm sorry.
Yeah, that's the lore, yes. Well, actually, if the superconducting phase is described by the Landau-Ginzburg theory, then exactly what I'm talking about happens. I mean, we did simulation. Basically, what you would look at is you would do one of these XPS experiments. And you would get some X-ray photon that would knock out a core electron. You would, in principle, leave the cloud around this ion. It could be in an excited state, or it could be in its ground state. And as a matter of fact, this effect actually exists, although it hasn't been put this way. When people do these kind of experiments in ordinary metals, there's a kind of a funny asymmetry in the shape of the thing. It's called Doniach something spectrum. Anyway, it's basically the same idea. When you hit this thing, you can kind of jiggle the conduction electrons. You can leave it in a whole spectrum of excited states. And that's what's responsible for this funny shape. Now, in the superconducting phase, I would say that the analogy is going to be you're going to have spectrum bumps in the spectrum. So the obvious thing to do would be to compare the spectra in the normal state and the superconducting state. And I've asked these ARPAS people, and they say it hasn't been done. And I looked in the literature myself, I couldn't find it. But that would be interesting to do.
Did you actually compute the value of this operator?
Which one?
The one that you said can grow linear.
Oh, yeah. I mean, for certain examples, of course, you can't pick every example in the world, but I have to, yeah.
Okay, so thanks very much. So I'm going to describe a somewhat different approach to this problem, which comes from trying to think of the confinement problem in the context of the gauge gravity duality. And the basic contention is that a confining string should be identified with the fundamental string for a suitable confining background. And that, I mean, I think there is some good evidence for this idea being a good approach. But if you describe this in terms of gravity, then that's only a good description if the gauge coupling of the QCD is strongly coupled. But if you want to understand it as in the ultraviolet, the gauge theory will become free. And then via the usual ADS-CFT correspondence, this will tell you that the gravity approach to string theory will break down in that approach. So in order to have a sense of what happens, you really have to understand the stringy description, not just in terms of supergravity, but in terms of some more honest string description. And honest string description means in terms of a worldsheet description. So the question is, what is the worldsheet theory that will describe what you would want to think of as the confining string background? Now, this is obviously a very difficult problem because the worldsheet theory you would expect to be generically very hard. The background is curved. It's sort of very far from supergravity. It's generally believed that in the context of four-dimensional gauge theories, you will have something like Ramond-Ramond flux. Ramond-Ramond flux backgrounds are notoriously difficult. There are very, very few results about it. And one has very little direct control of how to construct this worldsheet theory. Now, if you are, somebody this morning talked about the pessimist and the optimist attitude to the world. If you're a pessimist, then you give up at that stage. And if you're an optimist, you think that there should be something special about this worldsheet theory, because you see, the gauge theory is essentially free. I mean, you're looking at a regime where the gauge theory becomes free, and therefore, in some sense, becomes very simple. So nature would have to be very, very hard on us if the worldsheet theory was ridiculously complicated, given the fact that it's just meant to reproduce a free gauge theory dual description. So you could hope that somehow, I mean, you can be more specific. There are conserved currents, there's a large symmetry, and somehow you would believe that also the worldsheet theory should be highly symmetrical, highly special. Maybe it should be something like a free worldsheet theory that should describe free Young-Mills or free super Young-Mills. So that's sort of the basic idea of what we are trying to do. Now, obviously, at this stage, we are not yet brave enough to tackle a QCD. So our real aim is to find the worldsheet description that's due to free n equals to 4 super Young-Mills. That's sort of the string theorist's analog of QCD. That's in the realm of ADS-CFT. So you would believe that you have a realistic chance of finding the worldsheet theory. Well, maybe you wouldn't believe that you have a realistic chance, but for us, there is one main inspiration, which is the fact that we would claim that we've basically solved this problem in the lower dimensional analog of ADS-CFT. Namely, if you look at the ADS3, string theory and ADS3 cos S3 cos T4, that's believed to be dual to a conformal field theory that's related by an exactly marginal perturbation to the symmetric orbifold theory. So the symmetric orbifold theory we want to think of as being the analog of free super Young-Mills in 4 dimensions. And what we've managed to show is, or what we've managed to construct, is a worldsheet theory that reproduces exactly all the features of the symmetric orbifold theory. We managed to reproduce the entire spectrum, single particle spectrum of the symmetric orbifold theory in terms of a very specific worldsheet theory. And we managed to show that the correlation functions of that theory are correctly reproduced by this essentially free theory on the worldsheet in a somewhat non-trivial manner. I mean, these correlation functions here involve holomorphic covering maps. So there's a nice mathematics involved. And remarkably, this worldsheet theory localizes to configurations where exactly these configurations contribute. So this is, in my opinion, a very convincing and a highly non-trivial way in which this correspondence works. And this model is essentially a free field theory. I mean, the way I've written it, it involves many complicated symbols. You don't need to understand exactly what they are, but it has essentially a free field description and therefore realizes this sort of general contention that somehow the dual worldsheet description should also be very simple, essentially a free theory. So it works very, very well for ADS3. And then if you're an optimist, then you would think, okay, can we guess what's the analog for ADS5? And Rajesh and I made a proposal for this a little while ago, a year and a half ago. And we found some generalization of the ADS3 worldsheet theory that reproduces correctly the spectrum of free n equals to 4 supermills from a sort of natural worldsheet perspective. You see the spin chains appearing and all the rest of it. And while I think this is convincing on a certain level, it's also, there are certain things that are not quite working, or certain things we are a little bit unsure about. In particular, we have in some sense too many degrees of freedom for these worldsheet theories. And there must be some relation between the left and the right movers that cancel degrees of freedom relative to one another. And there are various things which we don't really understand and where we're a little bit stuck for how to construct this description from a more first principles perspective. So what do you do when you're stuck with a problem like that? Well, you tend to go back to the problem that you understand and you try to understand it even better. Because, I mean, that's the one straw you can lean on. So what our current thinking about this is that there's one thing that has been extremely successful for n equals to 4 supermills, and that is integrability. I mean, integrability methods have really shown that the ADS-CFT correspondence works and led to many, many remarkable identities. But in our ADS3 description, integrability played absolutely no role. There was not clear, I mean, at no stage did we use any argument based on integrability. We just calculated and it just matched. There was no place where integrability came in. And in fact, we have free field theory, but it's not clear what the analog of the integrable charges are in terms of this description. In fact, there's enormous confusion in the literature about how the integrability should work for the ADS3 story. There are people who propose integrable spin chains to describe the ADS3 background, but they've never managed to make contact with the symmetric orbifold spectrum. So somehow there is this sort of split minds in that there is the integrability community and there's the string community who thinks of the dual in terms of the symmetric orbifold, and it's not at all clear how these two viewpoints fit together. And in some sense, that's bizarre, because if you think about how n equals to 4 and the integrability started, it really started from the work from Linehan and Zarembo, who realized that the loop corrections to n equals to 4 have the structure of a spin chain. So what we feel we should do is we should try to do the same analysis for the symmetric orbifold, try to understand the perturbative anomalous dimensions of the symmetric orbifold in a language that looks like a spin chain, and then identify it with the corresponding quantities in the worldsheet theory to understand the role of integrability. And our hope is that this will also guide us. In particular, this is likely to relate left and right movers together in a non-trivial way, and hopefully will also guide us for how this will work for n equals to 4. So this is what we are currently working on. I think we've made some progress. We believe we understand essentially how this spin chain description works for the symmetric orbifold theory. We don't quite understand yet how this is related to all the other spin chain proposals, but I think we have a foothold where we can make some progress. So this is the one direction. The other direction I think that is interesting is that the ADS3 stories in some sense looks like a topological string, although it isn't a topological string. It's an honest string theory, but if you calculate it, what you find is that only very specific configurations contribute. So it behaves as though it's a topological string, but it's actually a full string. And it would be more interesting to understand this better. And in particular, you would think that that should somehow relate to this twisted holography of Costello and Gaiotto, which described the topological part of ADS5, which looks a little bit or a lot like the full ADS3 theory. And it's also very reminiscent of this recent progress of Rajesh and Nazenk, where they studied the Hermitian matrix model and they related it to some dual description. And the dual description involves this coset theory. And it's very similar to the SL2R that appears in our ADS3 worldsheet theory. So it would be very interesting to make contact with that. And that's another line of attack where you could hope to sort of understand the ADS3 answer more structurally with the view of understanding what to do for ADS5. So that's what I'm currently interested in and working on.
Yeah,
please.
This CFT and is about in ADS.
I mean, it's kind of holographic description, right? It is still, to me, sounds a little bit thingy in the sense that it is still correlated, you know, from the boundary to description in the bulk, right? And it's not like a local theory in the bulk, right? It does not look like, you know, UV completion of the gravitational sea, right?
No. I mean, it's a string theory, and it's obviously very, very stringy. I mean, it doesn't look very much like the geometry of ADS3 anymore. It looks, but it's a very specific critical string theory. And if you read your string books, you know what to do with the theory, and you calculate the spectrum. And
but then can you just measure something in on the boundary in CFT and to make conclusion about gravitational effects inside?
well, so how you would interpret this in terms of gravitation language is a difficult question, but it's an alternative way of describing this theory, and you would think that that is the correct description of the confining string.
This is infinitely curved.
Yes, the moon and the earth are all fit into my palm. This is the space is string size. So it's very, very stringy. There is no direct notion of classical geometry, but it has remarkably, again, a very simple description, which latches on as the sort of small radius continuation of this geometric picture, but has a very simple description, which then exactly describes this dual conformity. I mean, that's how it should be, right? And that's how it is. And in that case, you can actually identify this worldsheet theory, and you calculate. No, absolutely not. But in that context of ADS3 or ADS5, you would expect that is the picture. And you would expect there should be a worldsheet description, which will give you that theory at free super mills.
Okay, thank you. Okay, so for this panel discussion, I prepared a sort of wish list, things which I would like to understand, looking to the problem of confinement from the lattice side, if you want. And they are listed in order of increasing complexity. The first one, I should say, I almost understand. And the others are open issues. And the important point which I want to make, it is exactly here at the beginning, is that by now it is rather well understood that we have two different types of confinement and correspondingly two different types of FFT strings. The first one, which I will call QCD confinement, is the one which you find in ordinary non-abelian Young-Mills theories and also in the three-dimensional gauges in model. And it is described by a effective string which is dominated by the Nambu-Goto action, and we will see some effects. And the other side is instead the dual superconductivity model, which is known to describe for instance, the three-dimensional U1 model, which is somehow solved exactly, quotation marks. And I mean, the first thing which I think would be important to fix precisely is to be able to distinguish between the two. So to have a set of observables which are able to distinguish between these two modalities of confinement. The second point is, once we understand this difference, is trying to model the crossover from one to the other, and possibly comparing with the lattice simulations. We now have lattice simulations, but we do not have an effective string model yet. Then, increasing complexity, it would be nice to understand the interplay between the flux tube and the glue balls, and finally, the real important issue, find which are the degrees of freedom which generate confinement in the QCT string. So the degrees of freedom which play the same role which is played by monopoles in the U1 string. In the following, I will describe this U1 string as the rigid string, because this is the typical name which in the lattice community is used for this effective string. Okay, so the first say take-home message of this short presentation is that the tool of choice to distinguish between these two types of effective string is the shape of a flux tube. Because these two strings predict two completely different behaviors for the shape of a flux tube. So if one is able to measure with enough precision this quantity, then it is possible to discriminate between them. And the observable which is used to construct this effective thickness, this effective string shape, is this 3-point function in which, in the vacuum generated by two Polyakov loops, one measures the flux density using a plaquette. So this is a 3-point function. So it is difficult to evaluate, but it is not impossible. And it is much easier to understand the meaning of what I am saying looking to these pictures, to these cartoons. This is what I want to measure. This is a Polyakov loop. This is the anti-Polyakov loop. And this is the plaquette. And using the plaquette, I can evaluate the flux density within the lattice in presence of this quark-antiquark pair. So what happens is that if I do this calculation, this is the shape which I find. You see, there are these two huge peaks, which are due to the self-interaction of Polyakov loops, and then there is this nice shape here of the flux tube. And if you take a section here, you find this Gaussian-like shape, which one can use to obtain the width of a flux tube. But these are cartoons, but these instead are real simulations. This is simulations in the SU2 model in 2+1 dimensions. This is taken from a paper by Yotzi, Pepe, and Wiese. And you see, there is a perfect agreement with this Gaussian prediction. And this is a similar calculation which we performed a few years ago in the 3-dimensional gaugism model, which is again described by the same shape. So, what can we say on the analytic side on the shape of a flux tube? Then this is not too easy to evaluate using the full Nambu-Goto action of generic effective string action, but it's instead rather straightforward if we keep only the Gaussian approximation of the Nambu-Goto action, because it is essentially a free theory. And if we perform this calculation, this is what we find for the low temperature behavior. Low temperature means that the size of a Polyakov loop is much larger than the distance between the two Polyakov loops. And we find this well-known logarithmic increase of the width. And instead, in the opposite situation of the high temperature regime, in which the size of a Polyakov loop is much smaller than the distance, then we find a linear increase with this particular coefficient. Then one can check these laws, and indeed the result is in perfect agreement with the prediction for, say, the two-dimensional gauges in model. These are results obtained in the three-dimensional gauges in model, but one finds exactly the same behavior also for SU2. This is, yeah, sure.
For the previous prediction, where it will be nearly, we need to specify the boundary conditions.
Well, the boundary conditions are Dirichlet boundary conditions in this case, because I don't think so, because you can evaluate this also for periodic boundary conditions, and you find the same result. Sorry? Yeah, I think that one can. No. It's not exactly quantum mechanics, because still it is in this case simply a two-dimensional conformal field theory, a free two-dimensional conformal field theory with periodic boundary conditions. And what one is evaluating essentially is the two-point function in this conformal field theory when the 2 points are very near. So in a point splitting, say, regularization, they are epsilon far apart, one from the other. This is the way in which you evaluate this. Sorry? Yeah, the epsilon is this one. Yeah, exactly. And no, this is a rather standard calculation. I mean, it would require some time to recover it, but it is a rather straightforward calculation. In conformal field theory, the two-dimensional conformal field theory, a free bosonic theory. Okay, let me. And it works also for periodic boundary conditions. And this is what one finds in the high temperature regime. And you see there is this linear behavior, and the coefficient of this linear increase is proportional to the inverse of this quantity. So this is what happens in the case of the QCD string. Let me add a comment on this. Measuring these quantities is rather difficult for non-abelian theories. But if you look at abelian theories, then thanks to duality, it is very easy to obtain this kind of results. And this is the reason why I'm showing these plots for the two-dimensional gauges in model, because you can perform simulations in the dual spinizing model. Similarly, it is rather easy to obtain precise simulations for the three-dimensional U1 model, because also in that case, you can use duality to obtain these results. Sure. Actually, it's this one, because the inverse of the size of a lattice in the compactified direction is the temperature. No, it's 1 over NT. NT, sorry, NT is the size of a lattice, sorry. NT is this quantity, the size of a lattice in this direction. So it's the inverse of the temperature. So when I'm heating up the lattice, I'm simply squeezing it. And what happens is that the size of the width of a flux tube increases linearly with an angular coefficient which is increasing with the temperature. Exactly that. Again, exactly that. So still you have the behavior of the two-dimensional conformal field theory. Okay.
So I want to ask you if we consider Fox type, the hybrid,
So that is a good question. No, it is not related to the fact that in the three-dimensional gauges model, if you have a a second order phase transition, is completely general. So you can find exactly the same behavior in any non-abelian gauge theory and also in the post models. And so it's something somehow universal. Okay. So as I was saying before, you can do the same simulations also in the U1 model, so we can check if there's some difference. But the U1 model is pretty different because you see, thanks to the exact solution we have obtained by Polyakov of this model, we know that we have two scales in this model. The mass gap, the global mass, if you want, and the string tension. And these two scales are organized in such a way that if you are in the strong coupling regime, they are more or less of the same order. But if you go toward the continuum limit, the mass gap becomes infinitely smaller than with respect to the string tension. So the two scales scale in a different way. Okay. So, which is the effect of this model? Then we know that it is described by this dual superconductivity confinement scenario, and the main consequence is that the shape of a flux tube is completely different, because instead of a Gaussian shape, one finds, exactly as in superconductivity, an exponentially decreasing shape. So we have a new scale, which is exactly this mass gap, and which is usually called the London penetration length. So we expect a different behavior, and indeed, this is what we find. You see, this is in a log scale, so this straight line is showing that we have an exponential decrease instead of a Gaussian behavior. And this is pretty different from what I was showing you before. So these are two different effective strings, completely different. And so there are two different confinement mechanisms. One is understood, is the superconductivity one, and it is driven by monopoles. And the other one instead is completely different, and it is not driven by monopoles, as Jeff knows very well. Okay, let me add a comment on the second point. An interesting feature of the Nambu-Goto action of a QCD string of this logarithmic behavior is that we can define this critical distance RC, which in principle should be simply an ultraviolet cutoff, but instead, if you perform measurements, this quantity scales exactly as any other physical quantity. So it defines a new physical scale that you can measure. And it is a pretty universal scale. It takes more or less the same value in any lattice gauge theory in which this measurement has been performed. And its value is very similar, essentially exactly equivalent to the inverse of global mass. So in some way, and I don't know how, in some way there is a connection between the global mass and this scale that we find in this law. Okay, I'm running to the end. What happens of this logarithmic law in the U1 model? Then what happens is that instead of the string tension here in front of a logarithmic behavior, we find the mass gap. And also this scale is again proportional to the mass gap. So we have something which is very similar from this point of view, but pretty different, because these two scales are completely different with respect to the Nambu-Goto action. And since in the continuum limit, these two scales go to zero with respect to the string tension, at some point this logarithmic behavior will disappear. And indeed, we know that the superconductivity, dual superconductivity model has in the continuum limit a width which doesn't increase with the distance between the two sources. Okay, So last point, last slide. It would be nice to have some kind of analytic understanding of what's happening. And this is absolutely not obvious. The common law, up to a few years ago, following what Polyakov was saying, was the so-called rigid string. The rigid string is essentially can be written in this way. You have the standard number Goto action plus a correction which is proportional to the square of the extrinsic curvature. And a lot of papers were written on this this rigid string. However, we know now that this kind of correction is somehow in contradiction with the low energy universality theorem. So most likely this is not the right answer. Most likely this is not the right answer. A much more effective model is this one, which is pretty compatible with the low energy universality theorem. And in order to mimic the behavior of these two effective strings, one should choose these gamma-free coefficients, essentially proportional to the ratio between the square root of the string tension and the global mass. This ratio is essentially constant in all non-abelian gauge theories and also in the three-dimensional Ising model. More or less, it takes always the same value, which is more or less 1/3. But instead, in the U1 case, it goes to infinity. Okay, so what happens is that essentially we have a effective string description which is interpolating between the two confining strings. But the problem is that when gamma-free goes to infinity, we cannot use treat this term as a we cannot address the calculation of this term using a small perturbation with respect to the number Goto action. We need a completely different description, and obviously this is a problem. Even if I know that Andrea and Victor are obtaining remarkable results in this direction, still this is a problem. But we have a solution in principle. And this is the second take-home message. And the solution is trying to use the methods which was discussing yesterday Alessandro. So we can construct a machine learning program which is able to do this calculation essentially by heart, because we can use a normalizing flow from a Gaussian distribution to a Boltzmann distribution containing this parameter, and performing this way a non-perturbative calculation of this quantity, and possibly compare the result with the result that we have in the lattice simulations of the three-dimensional U1 model. So the second, if you want, take-home message is that if you have a tough problem, better to ask to your favorite machine learning tool to solve it instead of you. And then this was the last slide.
Low energy universality. You mean just that this extrinsic curve is determined irrelevant as long as
no, even stronger. The point is that this disappears because it is proportional to the equation of motion. This is the result which was obtained by Sergei and by and so on. So this term should not be there. Yeah. But you see, there are hundreds of papers which has been written. But by the way, I also wrote several papers using this term before we understood that it should not be there. And actually, this one is much more, so to speak, suited to address this issue. And without the low energy theorem, I think we would have never understood precisely what's happening here.
I think you trying to accomplish this, but in this one case, you're trying to track the relation with exponential like particle. This property to the motion is not compared to one event separation. So in the regime, energy is above the mass of the particle. That's not supposed to be effective to the theory. Really theory. The particle is coupled to the motion and it's applied. So there's no local to the action. Right.
I agree with you, should be something completely different. When you send gamma free to infinity, the type of effective string that you would expect should be completely different. In this sense, I agree with what you are saying. But I mean, in principle, I would be actually interested not only in the limit of the continuum U1 model in which gamma free is pushed to infinity, but in the crossover, because in the intermediate situation in which gamma free is large but not infinity, I have the results from the lattice simulation. So if I would be able to compare the two, then I mean, it would be an important result. It would mean that we are starting to understand what's happening in this game. But I agree with you. It is not correct to think of this as a perturbation of an Navier-Goto action.
Picture how the string appears. Let's say you want to take here the draws. That's very large in the direction. That much here eventually.
Yeah, this is exactly the idea we have.
I think we should
Sorry, sure. We can discuss later, but this linear increasing is exactly the way in which we understand the fact that at some point it disappears. Sorry. Sorry. A bit late.
No.
No, it's not like. It's best if you stand here in case you want to be recorded. If you're trying to avoid it, stand over there.
Okay. Well, thank you to Alexei for organizing this workshop. And I'll also say a few words about strings, and I focus on confining strings, meaning confining strings in QCD. Because, well, it's already clear from a bunch of talks which we heard here, QCD is a very rich subject. And there are infinite number of questions one may ask, but the theorist, it's very interesting that there is this limit when we take large n to infinity, where theory seems to simplify, and one can ask simplest possible, sharpest possible question about that regime. And you already saw this slide yesterday, well, this picture in Gabriel's talk. This picture was supposed, when we presented it first, it was supposed to illustrate that contrary to what sometimes one may hear, that somehow there are fundamental strings and there are QCD flux tubes, which are somehow not as fundamental. They're really intrinsic effective field theory objects. So this slide was supposed to illustrate the fact that, no, thanks to the presence of the NC, that parameter, that in the large NC limit, the confining strings become as fundamental as critical strings, in the sense that you have body theory, that there is scale set by the string tension and mass of the glue ball, and at low energies, as Gabriel already explained, there is a straightforward EFT description in terms of Navier-Goto action, but at this scale, this 2D description becomes strongly coupled, but still there is a decoupling of the 2D theory from 4D bulk. And at large NC, the regime of validity of 2D theory, regime of existence of 2D theory extends to much higher scale, which scales proportionally to NC, and essentially we can take limit NC first, and then obtain microscopic UV two-dimensional theory, which is decoupled from the bulk. And kind of the sharp question, which I would like to understand, is what is the physics of this 2D model?
Yeah, it's fair to say that it's up to the string, but it may not have a nice rigidity.
No, we know that this theory has nice limit. Well, we know essentially from lattice, if you wish. So from the existence of like we can measure, for instance, lattice allows us to measure finite volume spectrum of that theory with arbitrary precision at arbitrary large n. Energies.
You don't know that the true limit of short string exists. Which is the whole point of critical.
No, I'm not talking. Yeah, so I should be clear. I'm not talking here about short strings. I'm here talking. Yeah, I think either about infinitely long string or string wrapped around the. Well, okay, but at least again here I'm really talking about infinitely long string, and from the point of view of kind of two-dimensional observer doing scattering on this two-dimensional string, there is S matrix which exists up to arbitrary energies. So, right. So, yeah. So I fixed energy, energy first, and then I take n to infinity. That's right. Yes. And that describes and that defines my microscopic UV two-dimensional theory. So yeah, so that kind of I didn't ever use the slide to illustrate that of this, in the sense that there is a microscopic dynamical geometric object defined in both cases. So in that sense, confining strings are as fundamental as critical strings. But now I want to emphasize another aspect of this, which is actually was also mentioned by Gabriel yesterday. So namely that there is this slide also illustrates that there is a difference between kind of confining strings and fundamental strings, and it's exactly related to the existence of this window. One difference is well, it's what it said here that the Walsh theory kind of maybe technical, and that what makes this problem which we're discussing here interesting and hard. The Walsh theory is not integrable in the confining case, unlike the Walsh theory of fundamental strings, say, in flat background. And that's just a reflection of the fact that this theory lives in d equal 4 rather than d equal 26. So there is universal particle production. That's what makes it hard, this problem to address. But another difference, I think, in some sense, more fundamental or more interesting, is exactly so. There is this window, and in confining string case, we know kind of degrees of freedom. At least we think when we know degrees of freedom, which we should observe in this window, because this is window that response energies above lambda QCD. So it's below this n times lambda QCD, but it's maybe way above lambda QCD. So theory is symptotically free. So we kind of know degrees of freedom which we expect to find there. This should be just QCD patterns. And that difference with critical same case there kind of analog of these two scales would be string scale, and it would be something like string scale 1 over G string. But if one looks at the bullshit scattering, well, nothing really happens. There is e to the ISS matrix, like geometric phase shift, but kind of no, there is no new degrees of freedom which appear in this window. But in QCD case, we know that the correct description of physics in this window should be in terms of QCD patterns, and that gives us a hope to get around this problem that the series is not integrable. And this is kind of the summary. Again, we saw part of it already, but this is, I think, the short experimental summary by experimental. I mean, what we know from the lattice, or what we now know in d equals 4 and d equals 3 Young Mills currently. And what we know is that in d equals 4 Young Mills, there is the degrees of freedom which one finds are to both on bosons and with massive to the scalar particle with leading coupling. And in d equals 3, there is just single Goldstone bond. And kind of to connect to what I was just saying, this set of degrees of freedom is something which if you kind of very naive and they're just guided by symptotic freedom, that's exactly degrees of freedom which you would expect to find because on a string, because kind of the elementary excitations on a flux tube, they correspond to insertion. If you're young males, they just correspond to insertion of the only adjoint operator which we have, the field strengths. And so you can, if you have string which goes in z direction, so you can either insert fzx and or fzy, that would correspond to, in lattice language, that corresponds to attaching this placket that has Goldstone excitation by quantum numbers. And in 4 dimensions, one can also insert placket in the transport plane, and that's just operator with the correct quantum numbers that we describe that acts. And well, at least for now, and actually in the equals 3, there is rather non-trivial check of this in the global spectrum. For now, it looks like that's all what one finds so far on the lattice for confining strings. And to some extent, it would be surprising to find any other degrees of freedom, because it would mean there are other degrees of freedom on a string which are not partons of perturbative QCD. So the current situation is really that we have kind of, it looks like there's a good chance that when structured understand all the degrees of freedoms which are there, and they intuitively very nicely match the just what you expect from intuition from perturbative QCD. And I think the challenge is to establish kind of based on building up on this, to establish more direct mapping between dynamics which happens here and between these degrees of freedom and actual perturbative QCD dynamics. Well, I'll leave it here. I just mentioned there are a bunch of, there is some interesting, like this value of coupling. There's some numerology that it agrees with the value of coupling in integrable model when m goes to 0. And also in D equals 3, it turns out that that meta content is the meta content of a possible integrable model. And there are other appearances of integrability in QCD, like for instance, what Matthias mentioned earlier in his talk, in this calculation by Minahan and Zaremba. They actually started by doing calculation QCD, not in equal 4, and they found signs of integrability. And there is integrability in the FL regime. So the hope is that all these glimpses of integrable structure, they're not coincidental, and somehow they should be relevant for understanding existence and understanding of, well, this window.
That's right. Now you. I guess we can.
Please be careful with this stuff.
Yeah, that's right. No, no, no. It's just a beginning. Okay. So maybe we can take, if people had thoughts on what kind of questions they wanted to ask the individual speakers, especially some of the younger people in the audience, they have questions that they want to ask based on these talks. As a time, so.
In that picture you have that's the reason line, but it's in here. Well, let's suppose that supposed to represent as an operator which creates a string, right? Yeah, so that's the Wilson line. That's a straight line Wilson line. That's kind of, but the excited states of a string, they're created by, you can either geometrically deform the shape of the Wilson line, or kind of you can just describe it in terms of Wilson line where it's like no, I'm thinking in the context of lattice simulation, when one can say measures 2-point function. So that's how one extracts the spectrum of excitations of a string. One measures 2-point function of 2 Polakov loops, and kind of roughly speaking straight Polakov. So here only one. I'm drawing one of them, and kind of roughly speaking straight one. Right? Huh? It's the source, it's the operator which creates the wall shear, right? And if I insert here now this local operator, that would correspond to creation of the wall sheet with additional.
That will give you anything.
Sorry.
Yeah, if you, those days, the way the equation.
Well, this is the operator, quantum operator.
Maybe a later question is when you say makes a lot of sense from QCD viewpoint, maybe.
Well, I really just mean that long string can be thought of another way to think about long string if it's not Polakov loop, but in the context of static port, which was also discussed here, right? So it's interior of heavy quark meson, right? So you have two mesons and stretch them far apart. And we're asking what are the degrees of freedom, the excitations of a string at high energies, the degrees of freedom which you find inside that meson. And we know what are excitations inside hadrons, these are partons, right? And in this case, because it's pure glue, so it's only gluons. So and basically the elementary excitation, high energy excitation should be just gluons whose flux is screened by this fundamental flux loop, and these are exactly operators.
So you would think of these as having multiple insertions of these F's corresponding to these different things.
Right.
Yeah, I know a little more what this means. I know some people study these some loops with multiple insertions, or like in anechoic porcelain mills. And nowadays people study this a lot, like Wilson loops with insertions.
Yes.
That's it.
Yeah, exactly.
But then you can insert more things.
Well, yeah, but that would be multi-particle excitation, right? So that's.
He's saying that these are operators, right?
Yeah.
So you really have in mind exciting gluons from the string.
In the string, inside the string.
In the string, yeah.
In the string, right? Yeah.
If you show the thought, I mean, there's a spectrum from the lattice. There is the pseudo-scalar, and then there were these fire. What are these? Fire? The blue and the green.
Well, okay. So these are spectrum of two particle excitations on a string. So now one looks at what you should think about. You should think about long string, and these are the states. So these are excitation energies first of all. So there is a ground energy is subtracted. Right? That's why it's delta E here. And so you look at the states in Bogota language. It corresponds to states where there is one left mover and one right mover goes this way. And so different lights they correspond to there's O2 symmetry around the string. So in this sector there are three channels: this scalar, pseudo-scalar, in spin 2, and also the fact that this red light. So this is these different lines that effective string theory calculations for the spectrum. And one can see that red line is quite far apart from everything else, but also it's roughly independent. On horizontal axis here is the size of the string. So one sees that in the pseudo-scalar channel, there is a gap, which is roughly independent of this constant, independent of the size of the string, and which quite a bit deviates from effective string theory calculation, which work nicely into other channels. But on the other hand, the fact that it's flat, it looks like really a massive particle, and that's the plot which illustrates the existence. Yeah.
So okay, I'm going to ask you for. I have a question that's more generally for the quantum, not just to follow up to Sergey's talk, but if people want to keep asking about that. Yeah, maybe you should also. Yeah, I just want to comment on it. For sure.
I'm just to comment that Tim's question. So basically, the lowest state on that here, we don't include the operators that Sergey showed that they basically extend on the XY. So if you don't include these operators, this massive mode. Exactly. Yeah.
My question is maybe slightly provocative, so it's still anybody who's willing to answer. So, what are some research directions that you're not working on
maybe even not planning to work on that, you're actually excited about it. Without intending to offend anybody, I mean, it doesn't, it's not going to be a complete list that you do choose to answer. I'm just curious, like, what do you think? You want to go right to left?
Yeah.
You want to say that?
I would say for me, the most kind of in the sounds what Matthias was talking about this holographic CFT in connection with gravity. I mean, I would also look like kind of. I think there is development there, right? That kind of yeah, and I'm not sure how far it will go, but yeah, it sounds kind of more how to say kind of the bridge between our field theory and kind of gravity as a not just a local field. So no interest.
Too many things that I think very time. I think it's like to study the type of television that Jeff was discussing. But I think there is something happening and there is all this very interesting issue of the Caselle, as you know, it's kind of transitions which are not thermodynamic transitions, but are anyway transition in and also I would like to study really machine learning, not only using it but also understanding it.
Okay, well, I already said I was a partisan of the vortex model. So the work that I like quite a lot recently is the work of the Adelaide group, Weber and some other people. And they've been doing some beautiful numerical studies, which has been giving more and more evidence that it's general vortex thinking. And in that connection, I'd like to say something to Michaela. It strikes me that one thing that hasn't been looked at in this game that these guys have been doing is to investigate the width of the flux tube and the projected, that's what they do to project to the configuration. I don't think anybody's looked at the width of the flux tube within that picture. Is it the same as in the Bull theory or something else? I have no idea.
Well, there's lots of progress recently in understanding generalized symmetry. Iphone symmetry, which is highly relevant for string dynamics. I think it's very likely that bringing together these two questions closer may help. So let me, for instance, one example. Here is something that was too late, maybe something. Basically, in all these effective string theory descriptions we have, but nowhere appears the fact that these things we're talking that they carry DM centers. And for instance, natural, but there should be somehow, I think that should be important part of the story. And the simplest way to accomplish it would be to put something like 2D and mills on the string bullshit. It doesn't reduce any degrees of freedom, but it naturally gives the ability to talk about the and chart. So when we talk about the effective string, would it be something which is natural to do that it's in that window to argue that the string dynamics include also the annual theory, just by trying to talk about anomaly matching in very rough sense. So I should want to find the same symmetry.
Do you envision it's pure to the also there's a couple of other stuff directly?
Well, unclear, but somehow, well, in ultra low energies, probably just pure to the mills, but in this intermediate, that basically one wants to find the transition between these goldstone bosons at low energies and gluons at high energies, and that somehow makes it natural. Maybe this goldstone boson they become something like a joint scalars of the mills. These intermediate basis, something like that. So, but this argument can be made more precise just from the fact that we want to find the asymmetries and the symmetry that somehow that implies that it should be not trivial in topological theory, but there should be some sense like that. But that's just an example of trying to establish connection.
Was already worried nobody will mention them.
Turning the case of the confinement, this transition, has anyone looked at the entanglement entropy of the kind of order parameter, for example, in the Higgs space? The confinement phase of the studies, for example, by and collaborators, and it shows this interesting behavior where the short distances is very large and becomes much smaller when the size of the region becomes bigger than, you know, what about the Higgs space?
Not me, but maybe somebody has.
You want to comment? Thank you, Donald. Guys. Would it be possible to study the same kind of thing, but in the space and time?
Basically, if we can, you do it with
I would think you, in order to prove the energy with the phase, we would want something which is infrared.
Short distances, it's really those that their ends were fluent. But this is actually where the holographic calculation is to really see that. So what we're computing is the entanglement between the region inside the capacitor plate and outside. When the capacitor plates are closer, the scale, the huge entanglement.
Right, but I mean, it's something that should answer. We know that in the the question is about the infrared. So I wouldn't be surprised that they're different. So it needs to be something for the infrared. I don't know much about.
But still, this is like, if this transition is not there and they can. That would be a way to practice it.
Is there another way to compare it to other?
Yeah, we're going to figure
Yeah, because in the confining phase, there is this rapid drop that you in our and it's phase we don't know.
So anyone who has questions for the panel, or any questions? It's a big one. This I question that's it's time and space. That should be engaged.
I mean, the space-time picture is delicate because they're really string. The space-time picture is delicate because space-time geometry is gone. I mean, it looks it looks tiny. So,
Are there any estimate points?
well, the problem is the space, the string basically always is glued to the boundary of ABS. That's basically what happens. And that's how sort of the string is as large as the space, and therefore it basically lives on the boundary. And therefore, that's in some way how it reproduces the boundary degrees of freedom. It's sort of difficult to think about sort of.
But we have these ideas of theory, right? We don't need a space. Maybe this.
I mean, I think you can calculate everything you want on this logic theory. I mean, this is a solvable logic theory. If you tell me which capturing process you want to calculate, I can calculate it for you. I can also translate to you what it will mean from the boundary CFT. What I'm less sure about is what should be the geometric interpretation, given the fact that geometry is probably a poor concept at that point.
We can show some mimic the parallel the string thing, but it also said the grand scheme that it's the problems that not explain right, so sense. Right, we have like I said, we have hints that maybe you can speak on another thing. Like I said in the talk, we have hints of what if there's a fundamental description of the type of geometric amplitude, so it might look like in terms of taking a higher point string amplitude. And weird background with something, but we don't know. You can again, you can calculate boundary correlation without using string technique and the temperature and time on the platform. And you can also give the correlation goals in slightly scattering experiment. Taking you kind of super time going out of survey now. What is known about the string between the higher?
Oh, there are measurements. And there is data on the tensions.
But beyond the tension.
Right, yeah, well, because at finite end, there, because those higher K strings, they can bounce down stage of the fundamental stage, you can draw that way, and you expect to have massive excitations, and that will be fine. For instance, in 3D and mills for fundamental vacuum, there is no sign of any massive mode, but for higher K strings, one finds scalar modes, which one would expect because the series is a bound state. So, but these are all finite M effects. So here, in some sense, I'm interested in some question in strict planar limit, but this is a question interaction between strings and data.
Even in the strict planar limit, you could ask about a string with the order.
Oh yeah, no,
Those are very interesting. You could ask what do you do
no.
about effective. You deal with effective string theory, you can go.
Yeah, but again,
that was the whole point of what you heard.
oh, that's again, one would expect to find some.
So I have a kind of a common slash question. So I mean, I was very happy with experiment. Jeff said something about something conductors. So in general, I mean, so you had this long list of all the different confining theories and possibilities and your favorite picture. So I think it would be very good to think about what are these different, when you do have a favorite picture, how does it stress test against terminology in terms of predictions, well data from
at the moment,
foreign states and so on. It would be useful to thinking
Yeah, the experiment is computer experiments nowadays.
Yeah. So we do not need physics anymore.
Not good enough.
Well, the thing is about it, in fact, the depressing thing about it, really, is that the theory in a sense, QCD that is solved. Right? It's all, the talk, you know, you've got the whole spectrum, you've got confinement, you've got everything. So the computer obviously knows what it's doing. So, you know, I mean, these various ideas are all somehow tailored so that we get confined in one way or another. The stress test is,
But there's a wide range of phenomena which are very hard to describe. Very interesting and right. And then often you have to add a lot of ad hoc parameters and so on, which to actually describe an experiment. I think the challenge to this community is kind of progress.
No, but look, if you do not need experiment anymore and you can check everything on the latest, you know, why you would bother?
Yeah, so but any real time, any finite density, any real time process.
One issue that we have an experimental the model that people use to describe the sweeping of the harmonic states. They are using a form of the function, which is atomic. But in principle, you could tell them which is the baby, exact baby of the I'm not sure they would trust us. In principle, that is an experimental application which can be
kernel potential.
yeah, Condensed potential, yeah, it's somehow not. But
I
instead of
think we know it's not corrected for this. There is a law.
Yes, no, but also actually, I would say that there is an experimental development very much about this kind of exotic resonances.
Yeah.
And no, but even problems like remember the whole form of niche Voloshin is very much more like say the decay of say epsilon prime goes to epsilon into prime, for example. And there is some number of this type of decay where you're running exapair of prime, and the behavior of this spectrum as function of effective mass is the one which could not be understood. Okay, the people did not understand what's going on. So because normally you would think that this way prime would go to zero. I mean, would be distribution in this path. It did not work, say, for the system, and now they have more puzzles. But no, it's interesting. There are cases where it's okay, and there are cases where it's not okay. So no, it's just giving an example of a problem which is not resolved.
So something you said which is not quite right.
Yeah.
Is that you said that this G-2 is that the only prediction from the lattice. They also actually predicted some of these Charmonian states and C, which have been observed by
I see.
So that's actually
Okay.
in fact even more concrete.
I'm sorry. Okay, it's special because it interests me.
Those predictions are in
Yeah.
early stage.
Okay, yes, it says that.
But I think the concrete thing is that in modeling these things, the white junctions are important. The precise structure of these white junctions, how much energy they have. But I wanted to just say one thing about experiment. There is now a whole different experimental connection with a synthetic gauge field, right? Like people are trying to build these old atom devices. And there you like very precise understanding, say, of even 1 + 1 dimensional and 2 + 1. Will be tested.
Yeah, so the developments of 2+1 are especially exciting where when you have these you see clouds to small gauge lengths. So that's very interesting.
I think that's at very early stages, how good their synthetic gauge fields really are.
But to be cynical, is it different, that different from numerical simulation? Because computer is also
Yeah.
physical
Yeah.
device,
Yeah.
which also calculates something.
I think there's a big.
That's the
no,
sign
I
problem.
think there's a big difference. There is real time.
No, I understand, but there was complaint that
You- you-
simulation instead of doing experiments.
You could call that on computer.
Yeah.
Because here you start building dynamic.
Exactly.
Yeah, no, it's kind of very efficient simulation, but one can.
No, it's totally qualitatively different. I mean, I can ask questions about, what do things look like far out of equilibrium?
No, I agree
That's
with
something you
that.
can't
Like,
address.
somehow there was some happiness here that instead of talking about actual experiments, we talk about simulations.
Kind of fun
But-
computer.
Right.
Yeah, but there are actual experiments about God.
Yes.
Right, and they use things that we don't really have for models. Organization.
So, yeah, in some sense that you could say, well, I mean, to address what you said, well, you're in the computer, I mean, it is, on the other hand, extremely embarrassing that you can't answer very simple questions. Like, what is,
How does the proton actually look like?
and what does it look like when you boost it? So I can ask you this question, you center or receive, so this picture, what happens when you boost it? By energy, what does it look like? What is that? What does that distribution look like? Or when you fragment the string, what is the rate at which you produce kaons or some more complex states, lambda variables?
Could I answer a different question?
Sorry.
About cold atoms. I mean, it seems to me
Changing the
that,
topic.
apart from real time, you can also ask questions about that you can't answer quite easily on a regular computer. And that would be things having to do with finite density. Right? And not just QCD, but things like the Hubbard model. Can't handle on an ordinary computer. So that is one thing. Also, one thing about condensed matter.
But something
model.
like the Hubbard model, I think in sort of near term or midterm, you could really hope that that can be solved in one.
Yeah,
think
that is the idea,
yeah.
yeah. And it has somewhat the difference, I suppose, that we know QCD is the right theory. So in the hand round, we don't necessarily know that the Hubbard model is the right theory for high QC.
I think we know it's not.
Hoping that there are other things. We also have a dinner.
What about
They were arguing that it's an order to put it over the. Yeah, but that's thermal.
I'm not about that second order, but what if three dimensional? What if I want to study frequency relation? They actually have like the real composition. The real. People say second order, but I have to do composition. In second order, in the sense one of the great emission that kind of. Or in second order, only the zero mass bar.
You mean simulations that finite fields?
Yeah, because simulation very good.
So that is zero much more.
Yeah, that is second order. But the granite, I guess the first one. Yeah, frequency. Not one time. One time.
But. So that's a bit like also asking questions about, transport.
Yes. Another, if there is like leaches, if there is another. What's on about? I have to any.
What was the answer from me?
Apparently it's not known.
Yeah, I agree.
There is some scaling.
Yeah.
But now, but they know, they think.
No, but you know,
Oh, with experience.
Well, we know nothing from experience. Not for SU two, right? NC is three. Yeah, so the phase diagram. The phase diagram.
but I don't like say what I meant that for any equals three. It seems like it's kind of close to that word. Probably for any. That's what.
I thought. I don't know. For SU three.
For SU two, it's
First order, but if.
You're talking about QC theory and yeah, no, theory and next.
Yeah.
Yeah. Not legally for this, or the one, it's a technically person.
I think so like we are like situation that's great. We will take it for part of the action scheme. People have shown that the very fun is like become conforming with
Those are the crossover, maybe they're close to the critical. There's a critical, there should be a critical process there. But the DFN.
I'm correcting laboratory. The issue is the coordination of Vainshtein matter, which you have the confinement condition about the coordination of Vainshtein and the final matter of the confinement. And you can follow precisely the movement of the second order of transition final temperature toward the critical point of the dimension. And again, very different in the scientific process, but you can follow that. And
no signature of any variant.
So maybe a question for Roger. Here. What is known about the PCD prediction? People express interest in that? So that's also finite. How do you know that? There's no and zero of the part. Yeah, I'm asking more generally. What about a way to follow up? Yeah. Wait, is there some scaling? I don't know. So this you're talking about zero temperature. No, I'm talking about the team you play. Oh, it's a team you're playing. So yeah, so yes, that means the general idea is that you have this or you line first order. Exactly, determinate. And everybody says, oh, it's nice, right? Now Johar is saying, well, what I think it's zero. Exactly. Yeah, so I think that Rob Zarsky was supposed to have been here. It's
yeah, people say I think when it's height like Rajagopal and Milchek, I think height, they need height. If there is no information, you cannot refer it. I don't think that there is no character. Either the disappointment one, not the one that had a favorable. One can look at 5-4 theory with that people I'm sure have looked for.
I think you're right. Bob is right. So yeah, so you want to look at, for example, things like Q runs and then wave, right? Close to this critical endpoint and see how the behavior of the correlation.
Isn't the idea that you get some hydrodynamics, but with additional massless modes, that are related to the primary fluidity. So you have generic system with the hydromel. And if you have a CFT, it will have some extra mass. Or, yeah, one possibility that you could like this. Normal food and the top of that. Yeah, but isn't okay. There is some. You cannot even separate from ice and how do you end up 3D icing before it? Well, I thought that there was some theory of dynamic or critical phenomena that I don't know, but someone knows. But there's some Hockenberg.
Exactly, Alfred Hockenberg. So
Yeah,
it's a
it's like
classification of different universal
age model. So that limits my knowledge. The goals or better.
You mean something beyond Hockenberg out there?
You do have prediction for number near the tricrete. Near the curriculum.
Yes. There are predictions in terms of, how cumulants behave. So you can look at cumulants, say a variable number, higher cumulants, and it's predictions based on scaling. And there are these are real time.
What are the predictions from?
I think this is it from model.
Yeah, so I think this is kind of getting too specialized here. Yeah, this is super interesting. I myself, but maybe we should save some time for informal discussions amongst anybody who wants to meet up and chat with each other. Yeah. Yeah, so should we find out? Yes, any burning final questions to the panel? Okay, so thanks everybody.